Swayam Prabha. Digital India. Educated India.
Now, so far we discussed the theory. Let us start with the problem. So, example of a discrete sample space. Number 1, when a coin is tossed. So, a coin is tossed, actually ultimately we can get either head or tail. So, one becomes head, another becomes tail. So, what is the sample space? The sample space is h comma t. So, this way we can create what is the meaning of sample space. Next example, when a die is tossed. So, die having 6 faces, let it be 1, 2, 3, 4, 5, 6. I hope all of you. And then what is a sample space? Sample space is totally 6, therefore, S equal to 1, 2, 3, 4, 5, 6. Now, another example, set of all positive integer, you take it. So, set of all positive integer mean it start from 0, 1, 2, 3 and so on infinity. Now, it is a countable. Countable mean counting, see 0, 1, 2, 3 and so on we are counting, right. So, what is the sample space? In mathematical notation of a set is x such that x is a positive integer. So, this is a way we can express set of all positive integer is countable. So, keep it in mind this. Let us go with the further idea of continuous sample space. Now, you have a set, right. The set consists of 0, 2 from 0 to 2, 0, 0 0.1, 0 0.2 and so on up to 1.92. So, lot of real numbers between 0 and 2 is there, infinitely many. Now, suppose they may ask the sample space, what is that? S equal to such that 0 less than or equal to x less than or equal to 2. So, this way we can write with a set as a notation of a sample space x such that 0 less than or equal to x less than or equal to 2 in terms of the bounds. Once you understood this way of expression of sample space, I hope all of you can understand the further ideas about the set related to probability. Now, another example, you take a set of all real numbers x and y such that x lies between 0 and 1 and y lies between 1 to 2. So, what is the sample space? The sample space x lies between 0 to 1 and y lies between 0 to 1 to 2. So, that s equal to x comma y such that 0 less than or equal to x less than or equal to 1, 1 less than or equal to y less than or equal to 2. So, this way we can write a roster form and set builder form, we can define of a set. So, keep it in mind this. Let us go with continuous sample space in the example 2.1.4 and 2.1.5, and the following figure represent that. See, you take a real line axis x. So, it start from 0 and end with 1, therefore, 1 less than or equal to 0 less than or equal to x less than or equal to 2. This is a corresponding picturization. And if the both dimension respective to x as well as y we need, then we have a 0 less than or equal to x less than or equal to 1, and here 0 less than or equal to y less than or equal to 2. So, combined together we have a this type of the picture shows that this is a representation of a picture corresponding to the sample space. So, keep it in mind. Now, let us go to the next example. You take a coin, 3 coin, you take it, or a pair of coin tossed 3 times, both are same meaning. 3 coin tossed at a time, or one pair of coin tossed 3 times. So, what happened? Each toss is a functionally independent trial and forms a Cartesian product. Therefore, the cardinality of 3 tosses are 2 into 2 into 2 equal to 8, right, because each coin having the 2 faces, therefore, tail and head. Similarly, 3 coins we tossed, therefore, 2 into 2 into 2 into 2 equal to 8. Therefore, we have to write the sample space. See, for the 3 coins, say either it may comes H, that is all our head will come, or 2 head 1 tail will come, or 1 head 2 tail will come, or 1 head 1 tail and 1 head will come, or 1 tail and 2 head will come, or 2 tail and 1 head will come, and tail will come, and all our tail will come. So, these are all the possibilities. Therefore, that is called it as a sample space. So, keep it in mind this sample space. Let us go with the problem of probability of 2 heads. Suppose we want only 2 heads. So, from the sample space you check it out. See, 3 head out of 3 is 2 head is coming, right. Here HHT 2 head is coming. Here 2 head, HTH is 2 head. Here THS. So, this is the only possibilities. Therefore, out of 8, 4 possibilities comes. Therefore, number of favorable cases divided by total number of outcomes, that is the probability of 2 heads. I hope all of you understand that how the probability of 2 heads. Now, let us go with another example, a probability of both heads and tails. So, head also comes, tails also comes, right. What are the possibilities? HHT. So, here head is coming, tail is coming. Here head is coming, 2 tail is coming. Here 2 head is coming, 1 tail is coming. Here 1 tail and 2 heads comes. Here 2 tails, 1 heads come. Here 2 tails and THT is tail, head, tail will come. So, these are all only the possibilities. Therefore, favorable case is 6 by 8. So, in this way we can solve the problem of probability of both heads and tails. Now, let us go into the real time example. A telephone call occurs at a random between 9 am and 11 am. Imagine it. Hence, the probability that telephone call occurs in the interval 0 less than t less than or equal to t naught is given by t naught by 120. Thus, the probability of call occurs between 9:30 am and 10:45 am is given by the between 30 to 105, because we actually the random between 9, but the probability call occurs 9:30, therefore 30 to in between that 105, therefore we have to fix the range 30 less than t less than or equal to 105. Now, the rule is 105 are the upper and lower, subtract it 120, therefore 70 by 120 equal to 5 by 8 possibilities of this one will come. So, this is the way we can check it out, the probability of call occurred between the time. So, that is a more real time examples. And next example, the mortality tables give the probability density that a person who is born today, assuming that the lifespan is 100 years. Then we can write the corresponding function modeling is f of t equal to 3 into 10 power minus 9 into t square of 100 minus t square into u of t is the distribution function. That person will die at the age of t naught year is f of t naught equal to probability of t less than or equal to t naught, because he has to start from the age of 0, that is where he starts the born and then till the end of the life, therefore 0 to t naught, that is a fixing of the range, and he has the function of f of t is equal to 3 into 10 power minus 9 into t square of this will come. So, this shown in the figure like this. So, the range from 0 to 100, and in between that area under the shaded portion of the mortality density is like that 0 to 0.02. So, this is a way we can fix the probability. So, the probability that this person will die between the age of 70 to 80 is given by probability of 70 less than t less than or equal to 80. Therefore, you fix the what integral, the value, the range instead of 0 as 70 and maximum value is 80, substitute it, integrate it. So, you get the value of 0.15052, that is here explained. Here probability of 70 less than t less than or equal to 80 is can be written as upper f of 80 minus f of 70, or rather we have to substitute the integral 70 to 80 and then function value substitute it. Now, you integrate it. So, we have an integral of 3 into 10 power minus 9 and then we have 70 to 90 or sorry 70 to 80 and then what t square, therefore 100 t square, then minus t power 4 of dt will come, then you have to integrate it 3 into 10 power minus 9 of 100 into t cube by 3 minus t power 5 by 5 and then over the limit 70 to 80, then substitute upper limit into lower limit minus lower limit, therefore 100 into t is 80 cube by 3 minus 80 power 5 by 5 and then subtract with the 70, so substitute in the 70, therefore 100 into 70 whole power 3 by 3 minus 70 whole power 5 by 5 and simplify, you have 0.1052 will come. So, this is a way we can calculate a probability of the function from the range 70 to 80 of the person of the mortality ideas related to this. So, this is the density function in the figure 2.13 represent like this. So, this is the area of density under the area of a shaded portion is 0.1052. Now, keep it in mind this mortality distribution, the ranges from the domain is 70 to 80 and corresponding the maximum value is 0.942. So, this is the range of the domain, this is the range of the codomain. We can easily probability distribution can be designed from maximum to minus. So, 0.15052 is a corresponding possibilities. Now, keep it in mind, let us go with another example. So, tossing a fair die. Tossing a fair die having the 6 faces, toss it and then we shall calculate the probability that 3 has occurred condition on the toss being odd, right. So, odd is 1, 3, 5 and even is 2, 4, 6. So, total sample space is 6 and then 1, 3, 5 is a subset of this. Therefore, we shall define the following, A is the odd number, that is A of odd number and B totally B equal to 3. Therefore, what is the probability of A? Probability of A getting a possibility is 1 by 2 and probability of B is 1 by 6 because totally sample space is 6 for the general probability and then 1 by 6, whereas probability of A is what, only the odd number is 1 by 2 and the even A intersection B is a common point is 3 because both having 3, therefore, A intersection B is 3. Hence, probability of 3 over odd is probability of 3 by probability of odd. Probability of odd is 1 by 2 and probability of 3 is 1 by 6 and total number of possibilities divided by total number of outcome is 1 by 6 by 1 by 2 which is equal to 1 by 6 into 2 by 1 which is equal to 1 by 3. So, this way we can calculate probability of 3 over odd. Now, probability of 2 over odd is no possibilities because 2 is impossible event and an odd number has occurred. Also note that probability of 3 over 3 is only 1. Therefore, the conditional probability of 3 occurring the given 3 has occurred obviously equal to 1. So, this way we can understand the conditionality of one based other. I hope you can understand that how we can do with the normal probability and conditional probability. Now, we also find the solution using the concept reduce the sample space. Since we are giving that odd number has occurred, we can reduce the sample space from the set S equal to 1, 2, 3 and so on 6 and S1 equal to 1, 3, 5 as shown in the figure. So, the probability of 3 is reduced the sample space 1 by 3 as the previous result. Now, let us go another example. Consider a family of exactly 2 children. We will find the probability of 1 that both are girls, 2 both are girls given that one of them is a girl, third both are girls given that the elder child is a girl, 4 both are girls given that both are girls. So, the complication we can think about it. Now, the sample space has a 4 points. For first case both are girls is GG, second case both are girls given that one of them is a girl, therefore, one is girl and is boy, that is the meaning. and third one both are girls given that the elder child is a girl. Therefore, first one is boy, maybe girl, and both are girls given that both are girls mean BB. So, that is the meaning of sample space we can design. Here G stands for girl, B stands for boy. Therefore, capital B is both children are girls. Now, the conditioning event A will depend on the following. What is that event? V event is a sample space S, A. What is the probability of B, right? Therefore, it is a 1 by 4 because possibilities of the 4 points are GG, GB, BG, BB, therefore 4 sample space, and out of this 1 will come, therefore 1 by 4. So, because both girls are girls, both children are girls, therefore only 1, therefore 1 by 4. Now, you take an event A, one child is a girl. So, the reduced sample S1 is what happened? One child is girl mean and BB is ruled out. Therefore, it is GG, GB, BG mean both are girls, one is girl, another is boys, boys and girls. Now, what is the conditional probability? Here B over A. B over A is what? Here 3, therefore 1 by 3, that is all. So, that is the way we have used the conditional probability. Next example, event A is a elder child is a girl. So, in this case reduced sample space is what? Elder child is a girl mean GG and GB only will come. Therefore, it is a 2 possibilities, therefore, total number of outcome is 2, therefore, possibility is 1, therefore, P of B by A is 1 by 2. I hope all of you understand that how we can conditionally doing all these things. Next event is both are girls. So, the reduced sample space has only one point, namely S3 equal to GG, therefore, probability of B by A equal to 1. So, our knowledge of experiment increases by conditioning event, the uncertainty decreases and the probability increases the 0.25 through 0.333, 0.5 and finally to 1, meaning that there is no uncertainty. So, this way we can understand the beauty of this example. Now, another example, the game of craps as played in Las Vegas as the following rules. A player rolls 2 dice. He wins on the first roll if he throws a 7 or 11. He loses if the first throw is a 2, 3 or 12. If the first throw is 4, 5, 6, 8, 9 or 10, so it is called as point and the game continues. He goes on the rolling until he throws the point for a win or 7 for a loss. So, we have to find the probability of the player winning. So, we will solve this problem both from the definition of the conditional probability and the reduced sample space. So, this is the figure 2.22 shows that this is a figure 2.22 shows that, and then A die and B die and total and probability of corresponding total we have this, because throwing a 2 die and total sample space is 6 into 6 36. Now, probability of getting 2 is 1 by 36, probability of getting 3 is 2 by 36 and like that it goes all the displayed in the picture of die B corresponding to total. So, keep it in mind this. Now, this figure shows the number of ways the sums of the pips on the 2 dice can equal 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because first dice if you 2 dice are throw, suppose 1 will come, 1 plus 1 is 2 like that. So, first die and second die and first die you have to do that and all the possibilities may come the sum of the pips. So, the probability using that the conditional idea is the probability of winning the first throw is what? Probability of 7 plus probability of 11, then we have 6 by 36 plus 2 by 36. So, the sample space is 36, then simply add the numerator 8 by 36, then the possibilities is 0.2222. Suppose the probability of losing the first throw is what? Either it probability of 2 will come, 3 and 12 only comes. Therefore, already we know that probability of 2 is 1 by 36, 3 is 2 by 36 and probability of 12 is 1 by 36. Therefore, simply sum them you can 4 by 36, that is the possibilities. Now, corresponding picture you noticed, and then to calculate the probability of winning the second throw, we shall assume that the I, the point with the probability P, the probability of not winning any given throw after the first is given by R equal to probability of not I or not 7, then it can be written as 1 minus P minus 1 by 6. So, we compute the conditional probability that probability of win over I in the first throw equal to either P or RP or R square P and so on. So, it seems to be that it is a geometric progression that if you have what AR, AR square and so on is nothing but A into what by A, if it is infinite series A by 1 minus R. So, the same way here A is P and P by 1 minus R, and R is equal to what already we found out, that is 1 by minus 1 minus P minus 1 by 6, and substitute here. So, it becomes P by 1 minus of 1 minus P minus 1 by 6. So, 1 get cancel, and then minus into minus P plus P, and then minus into this is 1 by 6, therefore, P by P plus 1 by 6. So, it based on the infinite geometric series. Now, we can directly substitute what all the not I will come, either I equal to 4, 5, 6, these are all the possibilities, and directly substitute here. Therefore, P of win after point I equal to 4 is what 3 by 36 the whole square by 36, 3 by 36 plus 1 by 6, which is equal to 1 by 36. Probability of winning the point I equal to 4 is 4 by 36 whole square by the total number of ideas like P is equal to 4 by 36 by 4 by 36 plus 1 by 6, and substitute it, 2 by 45 will come, and probability of win after point I equal to 6, we have 5 by 36, the 5 by 36 whole square into 5 by 36 plus 1 by P, which is equal to what 25 by 396. Therefore, probability of win in the second or subsequent throw is P square by P plus 1 by 6. So, the probability of P of making the point is I equal to 4, 6, 8, 9, 10 is obtained from the figure, this figure. So, this is a way we can calculate it, what this problem. So, with a similar probability for 8, 9, 10, thus the probability of winning the craps is, the rule is probability of win equal to probability of win in the roll 1 plus probability of win the roll of either 2, 3, 4 and so on. So, probability of win the roll 1 is 8 by 36, and here 2 times of 1 by 36 plus 2 by 45 and 25 by 36, which is equal to 244 by 495. After simplification, you get the value of 0.4929. So, this is the meaning of the getting of probability of win. Now, using the reduced sample space, we can now use the reduced sample space to arrive at the same result in a simpler manner. After the point I has been rolled in the first throw, the reduced sample space consists of I minus 1 plus 6 points for I equal to 4, 5, 6, and 13 minus I plus 6 points for I equal to 8, 9, 10, in which the game will terminate. So, we can see the from the figure that there are 6 ways of rolling of 7 for loss I minus 1, that is I varies from 4, 5, 6, and the rolling of the point for a win, and 13 minus I equal to 8, 9, 10 ways of rolling. Thus, the probability of win in the roll 2, 3 such that I in the roll 1 is probability of W by I. So, the formula is I minus 1 by I minus 1 plus 6, where I equal to 4, 5, 6. If I equal to 8, 9, 10, then 13 minus I divided by 13 minus I plus 6. So, this way we can use the other way of solution using reduced sample space. Thus, probability of win over 4 is 3 by 9, probability of win over 5 is 4 by 10, probability of win over 6 is 5 by 11, and probability of win over 8 is 5 by 11, probability of win over 9 is 4 by 10, and win over 10 is 3 by 9. Hence, the probability of win after the first rule is probability of win by I into probability of I. So, the rule is the win after first rule is 2 times of 3 by 9 into 3 by 6, 4 by 10 into 4 by 36 plus 5 by 11 into 5 by 36. So, that after simplification we get 134 by 496. Similarly, probability of win is equal to what? 3 by 9 into 3 by 36, 4 by 10 into 4 by 36, 5 by 11 into 5 by 36, we have the corresponding values. So, and we have a comparative easy way to obtain the solution to the problem. I hope you can understand this, how to do that winning the problem of the numbers. Next example, we shall continue the example 2.18. So, 2.18 here discuss uh, 2.1 is a mortality tables gives the probability density that a person who is born to today assuming the lifespan of 100 years. So, this problem assuming it and keep it in mind. So, we are assuming that problem and find the probability that a person will die between the ages 70 and 80, given that this individual has lived up to the age 70. We define the events A and B as follows. A is a person has lived up to 70 and B is a person died between ages 70 and 80. Now, the required conditional probability equals the number of persons who die between the ages 70 and 80 divided by the number of persons who have lived up to the age 70. So, the rule is probability of B over A, this is called as conditional probability, and then the formula is probability of 70 to 80 and more than 70 divided by probability of t greater than or equal to 70. So, this is the formula of conditional. So, further we can write this as a probability of 70 t less than or equal to 80 by probability of t greater than or equal to 70, and already we discussed the mortality of the definition, substitute it. So, integral 70 to 80 of 3 into 10 power minus 9 into t square of 100 minus t square dt is a numerator, and the denominator t is greater than or equal to 70 means 70 to 100 and the same function, and already I explained how the integration you have to do that. Simplify, you get the numerator is 0.105 and denominator is 0.163. So, the result is 0.644. So, this is the type of analysis useful in setting up actuarial tables for the life insurance purposes. So, this is a real time application of life insurance purpose of finding the mortality rate of the person. Next, based on the independence, some more example we have to discuss. So, the probability of an ace on a throw of a die is 1 by 6. So, the probability of head on the throw of a coin is 1 by 2. Since the throw of a die is not dependent on the throw of the coin, so we have a functional independence and a combined sample space in the Cartesian product of 12 elements as shown in the table. So, 1 head and 2 head, 3 head, 4 head, 5 head, 6 head corresponding 1 tile, 2 tile, 3 tile, 4 tile, 5 tile and 6 tile. We assume that usual that all the 12 elements are equiprobable events and probability of ace and head is 1 by 2. Since there are the only one occurrence of 1 and 1 head among the 12 points as seen in the first row and first column in the table, using the equation 2.31, we have probability of 1 comma h is probability of 1 into probability of h, probability of 1 is 1 by 6, probability of h is 1 by 2, because 1 have 1, 2, 3, 4, 5, 6 out of this 1 occurred is 1 by 6 and head and tail only, the probability of head occurred is 1 by 2, therefore 1 by 6 into 1 by 2 is 1 by 12. Now illustrate this example, the independence coincidence, the statistical independence. Next example, two dice, one red and another is blue, are tossed. So these tosses are functionally independent. So we have the Cartesian product, 6 into 6 is 36 elementary event of the combined sample space, and the event is equiprobable, and the probability of B, event B is defined by the sum of the numbers showing in the dice of 9. There are 6, 3, 5, 4, 4, 5, 3, 6. This is the possibilities, and the probability of B is 4 by 36 equal to 1 by 9. Now we have a condition that the B with the event A defined as the red die shows the odd numbers, and the probability of A is 18 by 36 1 by 2. So we want to determine whether the events A and B are statistically independent. So these events are shown in the figure, where the first number is for the red die and the second number is for the blue die. So from the figure, probability of A intersection B equal to probability of 3, 6 or 5 by 4, 5, 4, therefore it is 2 by 36 1 by 8. Therefore probability of A into probability of B equal to 1 by 2 into 1 by 9, which is equal to 1 by 18, showing statistical independence. So the probability of B conditionally A from the point of view of the reduced sample space. So the condition even reduced the sample space from 36 points to 18 equiprobable points, and the event B over A is 3, 6 and 5, 4. Hence, probability of B over A is 2 by 18 equal to 1 by 8 equal to probability of B. Therefore, the condition event has no influence of B here, even though the events A and B are functionally independent, they are statistically independent. However, if another set C is defined by the sum being equal to 18 as shown in the figure, then probability of C equal to 5 by 36. Therefore, the events C and A are not statistically independent, because P of C into P of A equal to 5 by 36 into 1 by 2, which is equal to 5 by 72, which is not equal to probability of C intersection A, because probability of C intersection A is probability of 3, 5, 5, 3, which is equal to 2 by 18, which is equal to 4 by 72, they are not equal. So in this example, we have the case A and C are neither statistically independent nor functionally independent. So this is the picture shows that what we have explained in the set A and set B, and we have a pair of coin and corresponding the entries is explained, demonstrated, and see the previous one of the explanation, and followed with that what is the probability of C and what is the probability of C intersection A, and you may get the pictorial representation of answer of the possibilities of the throwing a 2 die, and you may get it. Next, total probability and Bayes theorem. Now we have a problem, 4 computer companies A, B, C, D supply microprocessors to the company. From the previous experience, it is known that the probability of processor being bad, if it comes from A, is 4%, B is 2%, C is 5% and D is 1%. So the probability of picking supplier A is 20%, B is 30% and C is 10% and D are 40%. So we want to find the probability that the processor chosen at random is bad. So this is the question. Based on that, we have to understand the solution to the problem. So let us define X as the event that the processor is bad. Now we find P of X from the conditional probability. P of X based on A is 0.04, that is given. P of X over B is 0.02. P of X over C is 0.05 and P of X over D is equal to 0.01 is given. And also given A is 20%, therefore 0.2, P of B is 0.3 and P of C is 0.1. Now P of D is also 0.4 given, because 40%. Now, according to the equation 2.43, we obtain the probability of x equal to probability of x over a into probability of b a, probability of x over b into probability of b, probability of x over c into probability of c, probability of x over d into probability of d. Therefore, we have what we know all the individual values, substitute it, you have 0.04 into 0.2, 0.02 into 0.3 and 0.05 into 0.1 and 0.01 into 0.4, and simply using the addition you can get it. So, this is a way we can use the summation of the total probability in terms of the conditional probability. So, I hope you understand that all of you that one is based on the other. Thus, the probability that the processor is bad is 2.3%. Another example, we will now continue the example 2.41 and find the probability that the processor came from the companies A, B, C or D, given that the processor is bad. So, using the result 2.41 and probability of x is 0.023 already found out, and we can write that based on the conditional probability of x over a, x depends on a is probability of x by a into probability of a by probability of x. This is a formula corresponding to conditional. Now, you know probability of x by a is 0.04 already found out, check it out in the previous problem. Probability of a is also given 0.2, probability of x equal to 0.023. So, you have to remember this problem, then only you can understand the following problem, and then substitute it, you have probability of x depends on a is 0.348. Similarly, probability of x depends on b is probability of x depends divided by b into probability of b by probability of x, which is equal to 0.02 into 0.3 divided by 0.023, the net value is 0.261. And probability of x over c is probability of x over c into probability of c by probability of x, which is equal to 0.05 into 0.1 divided by 0.023, which is equal to 0.217. So, probability of x by d is equal to probability of x by d into probability of d by probability of x. We have 0.01 into 0.4 by 0.023, which is equal to 0.17. So, the sum of the resulting probability is simply sum them, we have what 1, see beautifully comes, it will come 1, the whole maximum probability 1. So, it should be, because bad processor has to come only from any one of the 4 companies, and the resulting probability is 1. So, this is verified, and this is a very good example of doing that probability of the processor is bad or good. Next, another example, a communication receiver sends numbers 1, 2, 3 as a result of inherent noise is in the channel. So, the conditional probability of receiving 1, 2, 3 under the condition that 1, 2, 3 were sent as shown in the figure. Say, already we discussed the theory of priori probabilities. So, the priori probability of this one is 0.25 and 2 over s is 0.30 and 3 over s is 0.45. Now, let us start with 1. So, one may go have either 2 or 1 or 3. So, what is the corresponding priorities of this one is 0.6 here for 1 to 1 and 0.25 and 1.15 corresponding to 1, 2, 3. Similarly, for 2 we have 0.35, 0.55, 0.1, and for 3 to 1, 2, 3 is 0.05, 0.3 and 0.65. So, this is the way we can communicate the numbers 1, 2, 3 to 1, 2, 3 of the different channels, and we have a conditional probability corresponding to this is described. Now, the transition probability corresponding to this you have to write. So, 1 to 1. So, here 1 to 1, 1 to 1 is 0.6. This is what they written here. Similarly, you have 1 to 2 is 0.25. So, this is what they written here. Similarly, 3 to 1 and 1 to 2, 2 to 2, 3 to 2 1 to 3, 2 to 3, 3 to 3. This is what theory already explained, and this is the transition we have to write in terms of the table. Now, the method is probability that 1 was received is obtained from equation 2.43. So, you already discussed 2.43 here, right. So, we demonstrated already in the explanation of the theory, the 2.43, 2.44 and 2.43 is explained. Now, we have a probability of 1 over r is probability of 1 by that is 1 over r to 1 over s is into probability of 1 over s, and 1 over 2 is probability of 2, probability of 1 over 3 of probability of 3. So, therefore, you know the value of 1 r 1 s is 0.6 and probability of 1 over s is 0.25, that is previously explained, 1 over 2 is 0.2, that is prior probability. So, that you have to apply here. And similarly, from the data you have to apply the value of 1 over 2 is 0.3 and probability of 2 over s, the prior probability is 0.3 and that is apply here, and then probability of 1 over 3 and probability of 3 over s is 0.05 into 0.45 and add them, we have 0.2775. So, it is very interesting that the total probability how to calculate. So, from the Bayes theorem of 2.44, the posterior probabilities of 1, 2, 3 being sent, the condition on 1 received are found as follows. So, 1 over 1 that is probability of 1 over 1 of probability of 1 divided by probability of, that is a conditional probability. So, we have already explained. So, we have the 0.5405. Similarly, 2 over 1, 3 over 1 you have to calculate, and then prior probability is given. So, the sum you check it out, definitely it is equal to 1, and note that prior probability 3 was sent is 0.45 and after 1 has been received. The posterior probability is 0.0811, a very small probability. A similar posterior probability of 1, 2, 3 being sent condition 2, 3 received can be found. Next problem, Monty Hall problem. So, this classical problem is called it as a Monty Hall problem because the game show how the Monty Hall who designed this game. There are 3 doors A, B and C, and behind one of them is a car and behind the other 2 are goats. The contestant is asked to select any door and the host Monty Hall opens one of the other 2 doors and reveals a goat. So, he then offers the choice to the contestant of switching to the other unopened door or keep the original door. The question now is whether the probability of winning the car is improved if she switches or it is immaterial whether she switches or not. So, the answer counterintuitive is the sense that one may be misled into thinking that it is immaterial whether one switches or not. Now, we are going to analyze in 2 different ways. Now, we convert into mathematical analysis. So, let us analyze this problem from the point of view of Bayes theorem. We shall first assume that the host has a prior knowledge of the door behind which the car is located. Let us also assume that the host opens the door B given that the contestant's choice is a door A. So, the prior probability of the car behind the doors A, B, C are, that is probability of A is 1 by 3, probability of B is also 1 by 3, probability of C is also 1 by 3. Now, we can make the following observation. If the contestant's choice is the door A and the car is behind door A, then the host will open the door B with a probability of 1 by 2, since she has a choice between B and C. On the other hand, if the car is behind the door B, then there is a 0 probability that she will open the door B because her prior knowledge, if the car is behind door C, then she will open the door B with the probability 1. Thus, we can write the following conditional probability, the host becomes probability of B by A is 1 by 2, probability of B by B is 0 and probability of B by C is 1. So, this is the conditional oriented, we can analyze the mathematically the literary of the theory of the problem. Now, we can calculate the total probability of the host opening the door B is probability of B equal to probability of B by A into probability of A and probability of B by B into probability of B and probability of B by C into probability of C, and you know all the values, substitute it, 1 by 2 into 1 by 3, 0 into 1 by 3, 1 into 1 by 3, 1 by 2 will come. So, now using the Bayes theorem, we can find the posterior probabilities of the car behind the doors A or C, and B has already been opened by the host. The condition on B is P of A over B is P of BA by P of B equal to P of B by A into P of A by P of A B, and P of B by A is 1 by 2, you know already found. A P of A is 1 by 3, P of B is 1 by 2, substitute it, therefore 1 by 3 will come. Now, probability of C by B equal to probability of BC by probability of B, and by Bayes theorem, behind this using the theorem, P of B by C into P of C by P of B in the conditional probability. So, 1 into 1 by 3 by 1 by 2 is 2 by 3. So, the similar analysis for other cases of the opening of the door A or C. From the result, the above contestant must switch if she wants to double her probability of winning the car. So, the first choice A, the host opens B, and second choice A, therefore, the probability of 1 by 3, 1 by 2 into 1 by 3 equal to 1 by 6. So, for the first choice is A and host is open C, and second choice is A, therefore, probability of C equal to 1 by 2 into 1 by 3 is 1 by 6. And the first choice is B and host is C, then second choice is B, therefore, probability of C equal to 1 into 1 by 3 equal to 1 by 3. First choice is C and then host is B, then second choice is B, therefore, probability of B equal to 1 into 1 by 3, which is equal to 1 by 3. For not switching, choice A first and host B and second choice is A and win or loss win, then probability is 1 by 6. First choice is A and host is C and second choice is A, then it is a winning, then probability of C is 1 by 2 into 1 by 3 equal to 1 by 6. And first choice is B and host is open C and second choice is B and it may loss, and probability of C equal to 1 into 1 by 3 equal to 1 by 3. And first choice is C and host is B and second choice is B and loss, we have probability of B into is equal to 1 into 1 by 3 equal to 1 by 3. So, this way we can for using the for not switching. Suppose for switching, the first choice A comes, host B comes, second choice C and the win or loss is loss, therefore, probability of B equal to 1 by 2 into 1 by 3 is 1 by 6. So, first choice is A and host is opens for the switching and second choice is B and lost the game, probability of C is 1 by 2 into 1 by 3 is 1 by 6. Similarly, for third one choice is B, C and second choice is A and win or loss is win, probability of C is 1 into 1 by 3 is 1 by 3, and last one is C and host is B and second choice is A, win or loss is win, therefore, probability of B equal to 1 into 1 by 3 equal to 1 by 3. So, this is the way we can choosing for not switching and for switching. So, this is the analysis we can do, and further we have to analyze the heuristic analysis. In this case, we shall enumerate all the possibilities and determine which possibilities gives a better chance. Assume that car is behind the door A. The probability of A, B, C are once again probability of A equal to 1 by 3, B is also 1 by 3 and C is also 1 by 3. Therefore, the condition on the contestant choosing the door A, the host has two equiprobable choices of opening the door B or door C. However, the condition on the contestant choosing B or C, the host has only one choice, either opening C or B. Therefore, probability of B over A is 1 by 2, probability of C over A is 1 by 2, C over B is 1 by 1 and B over C is 1. Now, we can now enumerate the various win or loss probability for not switching and for switching, the table already explained. From the table 2.42 we can see that the probability of winning the car not switching is 1 by 6 plus 1 by 6 1 by 3. From the table 2.43 we can see that the probability of winning the car by switching is 1 by 3 plus 1 by 3 is 2 by 3. Therefore, the probability of winning the car doubles with the switching. So, this is the analysis we found out the meaning of the problem. That is it.